Hi, today we will learn about transistors. Yes, I know transistors are like Michael Jackson of electrical components and everyone knows about them. Although really, it's the capacitors who are the king of pop. I know you might be scared of transistors' complexity, but do you know what they really are? They're just a bunch of variable resistors, a bunch of electrical potentiometers. Well, if the potentiometer was on mushrooms. But really, they're just resistors you can adjust by providing them with a suitable input. Mind you, their resistance is not linear. You can't connect them backwards like regular resistors. There are different types and sponsors. Sponsors? Oh yeah, this video is sponsored by Brilliant. Learn complex math, science and computing easily using Brilliant's interactive courses from my link below. More at the end. Okay, how do I make it simple? There are many different types of transistors, main ones being BJT and MOSFET. In this video, I only talk about BJT. God, how do I make it simple? Okay, hear me out. BJT stands for bipolar junction transistor. It's just a name for a type of transistor that makes sense to me as much as it does to you. Don't worry about it. It is made of silicon semiconductors, same as a regular silicon diode. If you have watched my diode video, you know how diodes work. We have a positive or P and a negative or N semiconductor fused together, and that's a diode. Now imagine we also fuse an N to the P end of the diode or a P to the N end of the diode. And that's it, we have a BJT. If a PN junction was a diode, then these are like two diodes in series and act as such. Not quite. Yes, this behaves similar to two back-to-back diodes. But this is not equal to this. Also, it looks symmetrical on paper, but for example, this is an actual cross-section of a BJT transistor. Forget what you saw, it doesn't matter. Don't look at it. Look into my eyes. Don't panic. That cross-section cannot hurt you. We just want to know how the transistor behaves so we can use it. Let's focus on NPN. So it is kind of like two diodes. But although that's true, the transistor is designed such that in proper operation, only one of those diodes is in use. And so this is its symbol. The terminals for a BJT are called base, the terminal connected to the middle semiconductor, emitter, and collector. The reason behind the naming convention is nobody cares. Despite the fact that this is an NPN arrangement, flipping the collector and emitter doesn't work. Well, I've seen it work, but pretty badly and not to the component specifications. So no flipping. You saw the cross-section and it is not symmetrical. Don't look. Okay, so here's how it works. If you place a positive voltage across the collector-emitter terminals, then if you pass some little current through the base emitter diode by placing, say, 0.6 volts across it, magically, it is like opening a valve between CE and a much larger current flows from C to E. The more current into the base, the opener the collector-emitter valve gets, and so more collector current. That's why I said BJT is like an adjustable resistor. End of story. No, there is more. Let's give it a try. I have a generic 2N3904 transistor. I place a 1 kilo ohm resistor series with the base and adjust the input voltage. The voltage value across the resistor is equal to the base current in milliamps. I place a 1 ohm resistor from collector to a 5 volt supply. The voltage value across it is equal to the collector current. Base current is around half a milliamp and collector current is 66 milliamps. Change the base current to around 1 milliamp and the collector current is around 87 milliamps. So like I said, we typically have a large collector to base current ratio, which is a factor we called beta, or as more commonly used in data sheets, HFE for some reason. Just remember the names. And of course the emitter current is the sum of base and collector currents. But with the base current being much smaller than the collector current, we often assume emitter and collector currents are equal. But this beta thing is only almost constant if the transistor is on and is in active region. What is active region, you ask? Well, the behavior of the transistor changes based on the collector-emitter voltage. Let's measure. Same setup as before, but I'm providing a fixed base current. And instead of a fixed collector supply voltage, I have an alternating voltage between 0 to whatever. I measure the collector emitter voltage and collector current. Here you go, x-axis is VCE and y-axis is IC. You see the collector current rises with collector emitter voltage kind of like a resistor in this area up to around 0.2 volts. After which the collector current is almost constant for a large range of VCE. And then changing the base current, you can adjust the collector current. So this is what we have for the current versus voltage. A graph changing based on the base current. The region after this dotted line where the collector current is almost constant is called the active region. And the region where the collector current starts dropping because VCE becomes too small is called saturation region. The regions are named as such after nobody cares. I don't remember why, and this is not a history lesson, we just want to use it. In active region, the collector current changes so little based on the CE voltage that for simplicity, mostly we assume that the collector current is just constant. In electrical engineering, you'll notice that to keep sane, we simplify by ignoring small little things and design to get close to what we need, which is mostly good enough. And if it is not, we use adjustable components to fine-tune to almost exactly what we need. And this quarter area of operation is what the BJT transistor is designed for. If the VCE is pushed too high, the collector current starts to go up combined with the high voltage overheats and kills the transistor. If VCE goes negative, well, do you remember when I said BJT was like two back-to-back diodes? Well, a negative VCE results in the collector-based diode to turn on, pulling large currents from base like this, which is useless and bad, and we avoid bad. So far, this was all about the NPN BJT, but how about PNP? Well, PNP is just a complement of NPN with the diodes reversed and behaves exactly the same, except voltages and currents are in reverse. Here's its symbol. If there is around a negative 0.6 volts of base emitter voltage pulling current out of the base, we would have a collector current flowing, say, beta times larger than the base current. And the collector current to VCE graph looks like this. Voltage and current are just in reverse. And that's it. That's all you need to know for now. This much information is good enough for most your applications, and above that will get complicated in a hurry. We will get there if you prove yourselves worthy. For now though, we should know enough to throw some good circuits together. Let's do an amplifier. Well, I haven't told you enough to design a proper amplifier. But this doesn't stop us from my favorite process, trial and error. Here's the circuit. It's not a proper amplifier, but a simplified Class A amplifier, good for a one-off example. We already know it is an amplifier because it amplifies the base current to beta times at collector. But we want to amplify voltage. The input voltage goes to base and output comes out of collector with some gain. We don't know enough yet to calculate gain, it doesn't matter for now. First thing we do is we bias the circuit, which is setting up DC operating voltages and currents around the circuit, and the AC signals will ride over those DC values. This circuit is a common emitter, meaning that the transistor emitter is connected to a DC fixed voltage, which here is ground. We choose what are the best bias values for our operation. Starting from collector voltage, the best voltage for an amplifier is right in the middle of the supply rails. That way we get the maximum AC voltage swing without distorting the signal. See, the maximum a transistor can do is either being fully on or off, which means the output voltage here can go close to zero or supply voltage. So if the collector voltage is close to one of the supply rails, the output voltage clips at a lower amplitude. If our supply is 5 volts, then collector voltage is 2.5 volts, and for the collector current, let's pick 10 milliamps. So with 2.5 volt on collector resistor, this means the resistor would be 250 ohms. But closest I have is a standard 270 ohms, which means collector current is around 9 milliamps for the same 2.5 volts. Good! So now we can calculate the base current. Looking at the datasheet, HFE not only changes significantly by the collector current, even at a fixed IC there can still be a huge variation. That's why we should design a circuit that doesn't rely so heavily on the inaccurate transistor parameters. But anyway, let's assume HFE is around 200, so IB should be around 45 microamps, and so the base resistor would be around 97 kilo ohms. I have 100 kilo ohm though, and my resistors can be 5% off. Let's just put the circuit together. Okay, looking at the collector voltage, it's 2 volts or 3 volts across the resistor. So this means my collector current is closer to 11 milliamps. So for 2.5 volt, I should change the resistor to 227 ohms. Well, I have a 220 ohms. With 220 ohm resistor, I have closer to 2.5 volts. So now I feed the signal into the base. Issue is the DC component of a signal generator can load the base voltage and throw the bias off. So I add a 10 microfarad capacitor between them to isolate the DC voltages while the AC will get through. One thing though, how big can the input signal be? Base emitter is a diode and its voltage versus current is like this. If the signal is too large, the base current is not linear and the output signal is distorted. For minimal distortion, we should keep our signal small so the base current remains relatively linear. Here I have a plus minus 5 millivolt input to the circuit, and if I probe the output, that is on a 2 volt scale, you see I have a sine wave inverted from the input riding on a 2.5 volt bias voltage. Now if I get rid of the DC component, change the scale, you see for the 5 millivolt peak input I'm getting around 300 millivolt peak output. So I have a gain of around 60. I could connect a microphone to it and amplify my voice. Well, I'm using a subwoofer speaker as my microphone. Ella, Ella, umbrella. Now only looking at the output voltage, if I increase the input, you see we start seeing the distortion I was talking about more and more until the signal hits the rails and clips. See, I'm happy we got this far in ElectroBOOM 101. I feel like I can throw circuits together with more confidence, knowing that if you follow the series, you can figure out what I'm doing. And of course, don't forget about my sponsor, Brilliant. I always recommend it to everyone because I see how interesting and interactive it is and how it keeps people engaged in learning anything from logic and computing to science and math. Brilliant has thousands of interactive courses from intermediate to advanced levels with an exclusive new one added every month. My daughter engages well with logic and analysis courses and quizzes while I kick myself trying to learn some advanced math. You can start for free by visiting brilliant.org/electroboom or click on the link in the description. And the first 200 of you will get 20% off Brilliant's annual premium subscription. Trust me, this is something you or your loved ones should do and will enjoy spending time on. At your own convenience, from the hours you spend on your phone or computer every day, spend 30 minutes at Brilliant. Their interactive courses and quizzes are like fun challenges that will help you immensely at school, work, or interview by teaching new skills or refreshing your fading memory. Do it now! And thank you for watching.